Alright, this video is for Unit 5, and this is our fourth and final lesson of Unit 5. So we are wrapping up polynomials. Before we get into our new things for today, I want to remind you about these sorts of problems. We saw some of these last year. So we have this first polynomial right here. It is a degree 3 polynomial, and we have a little graph of that polynomial. So when we look at this graph, we can tell a lot about its roots. First of all, it's a degree 3 polynomial, so the fundamental theorem of algebra guarantees that we will have 3 total complex roots. That includes all types of roots. We can see from the graph the real roots. And this graph, we can see that the function has one real root, and it happens to be at the value 1, but it has one real root. That means that since it's degree 3 and only one of the roots is real, that means this one must have 2 non-real roots. That's what we're going to do today, is find those non-real roots. So let's look at this next one. This is also a degree 3 polynomial. So that means it has 3 total complex roots. If we look at the graph, though, we can see that this one has 1, 2, 3 real roots. That means it doesn't have any non-real roots. All 3 of the roots are real in this case. This is an interesting polynomial. It looks like one of the roots is 6. The other 2 roots, though, aren't so nice. We have one that's between -2 and -3, and one that's between +2 and +3. Today, we will find those irrational roots, the ones that aren't so nice. This last one is a degree 4 polynomial. That means that it must have 4 total complex roots, and you can see by looking at the x-axis here that it does not have any real roots. It has 0 real roots. That must mean all 4 are non-real. So today we're going to be focusing on non-real and irrational roots. What we're going to be doing today in a lot of ways is very, very similar to what we did last time. The difference is that last time our answers were in this portion of the number system. We had roots that were whole numbers or integers or maybe rational numbers when we had roots like 1/3. So all of our answers in the last lesson came from this section of our number system. Today, we're going to be focusing on polynomials that have roots in the irrational number section and in the non-real number section. The non-real numbers, in case you're forgetting what those are, they are numbers that have an imaginary part, like 3 plus 2i. They're ones that have i's in them. Irrational numbers are numbers that can't be written as decimals. In most cases today, we'll see irrational numbers as square roots and things of that nature. Okay, so just remember, the fundamental theorem of algebra means that a polynomial has exactly n roots if it is degree n. We can find those roots if it is factorable by factoring. If the roots are irrational or non-real, we typically can't find them through factoring, so we need another method. And I don't know if you remember, but when you're working with polynomials, if they are not factorable, one of our solution methods is our good friend, the quadratic formula. Quadratic formula, I can spell formula, is back with a vengeance today. So let's try this first problem, example 1. What are the exact zeros of the polynomial function shown? Well, here's our function, and we have both the equation right here, x to the third plus 4x squared minus x minus 10, and we have the graph of the polynomial. And we want to know what the zeros of that polynomial are. Well, for starters, we know that it must have 3 zeros. So when we're writing our answer to the problem, it should look something like x is this, or this, or this. We have 3 roots. So that's what our answer needs to look like, the 3 roots of the polynomial. Well, when you look at this graph, you should immediately be able to see one of the roots. Right here. We know that one of the roots of the polynomial is -2. The other ones, though, aren't crossing the x-axis at integer points, so we can't be sure of what those values are. We could estimate them, but the question says it wants to know the exact zeros, so we need to be a little bit more precise than just estimating. Well, if we know one of the roots, just like we learned last time, we can use that root to divide the polynomial. And we'll use synthetic division for this. And we know it has a root of -2, so we'll go ahead and use that in our synthetic division. Drop down that first column, multiply by -2. So 1 times -2 is -2. We'll write that in the next column and add this column up. And now we'll multiply that number by -2. 2 times -2 is -4. And we write that in the next column. And we add that column up. And -5 times -2 is +10. We put that in the last column. And we add that column up. If we were right about -2 being a root of the equation, we should have a 0 remainder here. So this synthetic division right here confirms that we were correct about -2 being a root of the equation. Well, remember when you do synthetic division, the result of your synthetic division is a polynomial that starts 1 power less than your original equation. So this original equation was power 3, so this result here is power 2, 1x squared plus 2x minus 5. And this polynomial is going to give us those other 2 roots. Now, last time when we were going through this process, we found that we were able to just factor this polynomial to get those other 2 roots. But hopefully you recognize that there's not a way to factor this one. There aren't factors of 5 that could be used to get a 2x as that middle term. There's just no combination that works. So instead of factoring, we have to turn to our old standby, the quadratic formula, to help us get those other 2 roots. So x must be equal to -b, so that would be a -2, plus or minus, we've got our square root. Here's b squared minus 4 times the a value times the c value. Let's see if I can give myself a little more space here. Okay, and that, of course, is all divided by 2a. So as you're using the quadratic formula, I want to remind you that we don't want to get a decimal value for our square root. So think about what the argument of your square root is. Think about what number is inside that root, but don't type that root into your calculator. For one thing, there's not a way for your calculator to handle that plus or minus symbol. Okay, I'm going to give myself a little bit more space. So if we simplify that radical a little bit, or if we figure out what is inside that radical, we have -2 plus or minus the square root of, and you can use your calculator to figure out what's inside the root. Just please remember, don't put the root in. 2 squared is 4, and then we have a -4 times 1 times 5, so that would be plus 20. So we have square root of 24. Now, if that radical is simplifiable, you do need to go ahead and simplify it. Thinking about the square root of 24, we want to think about a way to factor that number 24 that utilizes a perfect square. 24 is the same as 4 times 6. We know what the square root of 4 is. It's 2, but that 6 is still inside that root. So root 24 is the same as 2 root 6. So we could rewrite this as negative 2 plus or minus 2 root 6 all over 2. And there's a lot of factors of 2 there. It looks like we could reduce this to 1, and we could reduce this one to 1. So it's going to be negative 1 plus root 6 and negative 1 minus root 6. Now it's okay for you to leave it in the form with the plus or minus symbol. You could write here negative 2 and negative 1 plus or minus root 6. I just want to make sure that you understand that that plus or minus symbol does mean negative 1 plus 6 and negative 1 minus 6. It means we have 2 roots there. So our 3 roots are now found. Now, I think sometimes we look at a number like negative 1 plus root 6 and maybe we don't really understand where that would show up on the graph. If you ask your calculator, what is negative 1 plus the square root of 6, your calculator says that this is around 1.44, etc. And if you typed into your calculator negative 1 minus the square root of 6, it would tell you that that's around negative 3.4494, blah, blah, blah. So if you look back at the graph at the top here, you can see that those 2 values are on the graph. Here is the first one. This is negative 1 plus the square root of 6, which is about 1.44. This value over here is negative 1 minus the square root of 6, which is about negative 3.44. Irrational ones do show up as roots on the x-axis. It's just that to get their exact values, you do need to use the quadratic formula. Otherwise, you'd just be estimating. Okay, super fun, right? You love the quadratic formula. Let's try another one. One of the factors of this polynomial is x minus 4. We want to make a list of the roots of the function. So again, our answer is going to be a list of roots. And because it is degree 3, we know that there are 3 roots. Well, if we know x minus 4 is one of the factors, we already know the first root is 4. Now we're going to use that root to help us find the other roots. We'll use synthetic division. So we know 4 is a root of the function. So let's divide using that root of 4. So we drop that first coefficient down, multiply by 4, put it in the next column, add that column up. This is a little tricky right here. People get tripped up by the zeros sometimes. 0 times 4 is 0. That's okay. And now we add up that column. Negative 7 plus 0 is negative 7. And we just continue on our way. So don't let that 0 trip you up. You treat it the same as always. Negative 7 times 4 is negative 28. And we got a remainder of 0 just like we were expecting. So you got to decode your coefficients there. Original equation is degree 3, so this is a degree 2 equation. That's my x squared. This would be x. This one has 0x. So it just looks like x squared minus 7. Our other 2 roots are going to come from this. We're trying to solve x squared minus 7. You could, of course, use the quadratic formula for that. I'll show you that. X equals negative b. This has a b value of 0x plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. Well, we don't really need that 0 there. And it looks like our radical is going to be root 28. And again, you can just get that from your calculator by not typing in the root, but just typing in the inside of the root to get that 28. And we need to think about that root 28 and how to simplify it. Well, 28 is the same as 4 times 7. We know the square root of 4 is 2. The 7 gets left inside the root. So we could simplify this to plus or minus 2 root 7, all divided by 2, and you could reduce the 2 so that you just have plus or minus the square root of 7. That would be the other two roots, a positive root 7 and a negative root 7. So we found the three roots of our equation. Now, some of you may have noticed that you could probably solve this equation without using the quadratic formula. The other method you could use is just to try to directly solve. So add the 7, x squared is equal to 7. When you take the square root of both sides, you have to introduce that plus minus symbol. So you get x equals plus or minus 7. Sorry, square root of 7. So this method works when you have 0 as your b value. So if you like that method better, that is fine to solve it that way. There's nothing wrong with it. Okay, so we completed practice A. We found the roots were for root 7 and negative root 7. Well, I don't know if you noticed, but when we use the quadratic formula to help us find these irrational roots, they always come in pairs. And the reason that they're coming in pairs is because it's built right into the quadratic formula that there's going to be a plus and a minus. So if we know that 1 plus the square root of 2 is one of the roots of the equation, then we know another root of the equation as well. They come in pairs. So we know that 1 minus the square root of 2 is also one of the roots. Now, it's only the root that changes sign. In this case, the 1 in front of that root did not change signs. 1 plus root 2, 1 minus root 2. If the square root of 10 is a root, then another root is negative square root 10. The root changes signs. If 2 minus root 6 is a root, then 2 plus root 6 is a root as well. And just in general, if you have a number like a plus the square root of b, if that is a root, you know that a minus the square root of b is also a root. They always come in pairs if they have a radical. So here's a question for you. A polynomial equation with integer coefficients has the roots 1 plus the square root of 3 and negative 11. Find two additional roots. Well, we don't even have the equation, but that's okay. We know irrational roots come in pairs. If 1 plus the square root of 3 is a root of this polynomial, 1 minus the square root of 3 is also a root of the polynomial. If negative square root 11 is a root of the polynomial, positive square root 11 is also a root of the polynomial. So we have found our two additional roots. Second part says, what is the lowest degree that this polynomial could possibly be? Well, we talked earlier about the fundamental theorem of algebra and how the degree of the polynomial and the number of roots is the same. If it's degree 3, it has 3 roots. If it's degree 5, it has 5 roots. Well, I know 1, 2, 3, 4 roots. So this has to be at least degree 4. If there are other roots that aren't being mentioned, perhaps it's higher than 4, but it absolutely has to be at least a degree 4 polynomial. Okay, another one to try. A polynomial equation with rational coefficients has roots 2 minus square root 7 and square root 5. Find two additional roots. So 2 minus square root 7 is one of the roots. we know that means it must also have the root 2 plus root 7. Root 5 is another root of the function. We know that means negative root 5 is another root to the function. So we have found 2 additional roots. Okay, polynomial equation with rational coefficients has roots 1 plus the square root of 7 and 8. Do you know any additional roots? Well, we know that if it has an irrational root, it will come in a pair. So we know 1 minus the square root of 7. However, integer roots like 8 doesn't have a partner. And we've seen this before. We've looked at equations where the roots were 3, negative 5, and 2. Having a root of 3 doesn't guarantee it has a root of negative 3. Integer ones don't come in pairs, only radical ones. So the only additional root we know is 1 minus the square root of 7. Integers don't have partners. Okay, so this next part says, what is the least possible degree of the polynomial? Well, the least possible degree would be, well, we know 1, 2, 3 roots, so this has to be at least a degree 3 polynomial. And it would look like a regular polynomial. It comes through at the value 8. 1 plus the square root of 7 and 1 minus the square root of 7, it would probably look something like this, where this is 1 plus root 7 and over here is 1 minus root 7, whatever value that is. Okay. And now for something a bit more complex. Here's the first joke of the day. It's an awesome one, so I hope you look at it and read it because it's really funny. Okay, example 4. What are the roots of the function shown? So here's this lovely cubic polynomial. Cubic polynomials can look like this. They do sometimes. I want to know, what are the roots of this polynomial? Well, I look at that degree. I see that it's degree 3, and I know that absolutely means it has to have 3 roots. Our job is to figure out what those 3 roots are. Looking at this graph, I'm hoping, and you should be able to by now, look at that graph and immediately see one of its roots is negative 5. We can see it has an x-intercept at negative 5. That means one of the roots of the function is negative 5. Let's use that root to find the others. We'll just use some synthetic division to divide that root out, or divide by that factor. So here's our setup. We drop down that first column, multiply by negative 5, and put it in the next column over. We add this column up and we get negative 4. Negative 4 times negative 5 is positive 20. We put that in the next column and we add this column up to get 85. We multiply 85 by negative 5 to get negative 425. And when we add that up, we get 0. That means we were correct about a root being negative 5. That's confirmation that our assumption that negative 5 was a root is correct. So the synthetic division has a result of x squared minus 4x plus 85. Now normally, last lesson we would have tried to factor this, and we should always, of course, try to factor and maybe think about the number 85 for a second. 85 is 5 times 21, and you know, you can play with it in your calculator. 3 times 35, that seems off. I need my calculator. 85, oh goodness, sorry, not 5 times 21. I can do math in my head. 5 times 17, and both 5 and 17 are prime numbers, so the only other possibility would be 1 times 85. And you know, we have got a middle term of -4, so it looks like there's not a combination that would cause this to be factorable. So we can't factor it. Now, another clue that we wouldn't be able to factor it is by looking at that x-axis and seeing that there's only one real root on that graph. So not factorable. If it's not factorable, we have to use the quadratic formula. X equals -b. Well, -4 is +4, plus or minus the square root of b squared. Be careful if your b is negative, you need it in parentheses, or you will have a sign error that will cause you to get the incorrect answer. So b, -b plus or minus the square root of b squared minus 4 times a times c, and that's all divided by 2a. So let's figure out what's inside that radical. Again, don't put the root into your calculator if you're using your calculator to evaluate this. Only put those quantities inside the radical. Oops. Just calculating that, and it's -324. Well, if you get a big number like 324 and you're not sure, I would first try just to see what the square root of 324 is. Now you know, or you should know by now, that the fact that this is let me get a smaller, the fact that this is negative right here means that our answer is going to have an imaginary part. It's going to have an I. But if we think about just the square root of just 324, if you tried that out in your calculator, you would find that it's 18. So if our square root is -324, that just means we're going to have 18i. Again, square root of a negative gives me that imaginary part. So we have 4 plus or minus 18i, all divided by 2. So if we go ahead and divide those parts by the 2, we get 2 plus or minus 9i. So our other two roots are 2 plus 9i and 2 minus 9i. Again, you don't have to separate it out into the plus and the minus one. I'm just doing that to help you see that we have found all three of the roots of the function. It has one real root, and it has two that are non-real, that have an imaginary part. Okay, let's try another one of those. One of the zeros of the polynomial function f of x is 2. What are the other zeros of the function? Well, it gives us the first 0, 2, and we can use that to divide and get the other 2. So let's see, drop that first number down, multiply it, add up this column, -6, multiplied by 2 is -12. Add up this column, 70, and -12 is 58. And when we multiply by 2, we get positive 116. And when we add that up, we get 0. So that's good. It confirms that, you know, we did our synthetic division right. We were expecting to get a 0. So if we decode that answer, those coefficients, this would be an x squared, this will be an x. So we have x squared minus 6x plus 58. Now when we get to this point, we should always try to factor, and you know, on your test it's not going to be separated into a factorable and an unfactorable section. You're just going to be working, and you're going to have to decide what your proper next step should be. Well, in this case, if we're thinking about the number 58, obviously it could be a 1 times a 58. 2 definitely goes into it because it is an even number. It's 2 times 29. So 2 and 29 are both prime numbers. There's no other combinations for 58, and if you weren't sure, you could try a couple things, but that's the only combinations. So you can see that we're not going to be successful at factoring this with a middle term of -6. So we're going to have to use the quadratic formula. X equals -b, -6 is +6, plus or minus the square root. Be careful when you have a -b to get it in parentheses. B squared minus 4 times a times c, and that's all divided by 2 times a. So if we figure out what that radical is, it is -196. We know that negative means that it's going to have an imaginary part. It's going to have an I. So let's just think about 196. It's probably worth just checking that root. 196, the square root of 196 is 14. So in our problem, we have the square root of -196. That's just going to be 14i. So we have 6 plus or minus 14i, and that's all divided by 2. So our question said, what are the other zeros? The other zeros are, if we divide the 2 out of both of those terms, we get 3 plus or minus 7i. Again, the 3 comes from the 6 divided by 2, and the 7 comes from the 14 divided by 2. So here are other zeros, both non-real. Okay, well, we find these complex roots by using the quadratic formula. Because that plus or minus symbol that is part of the quadratic formula, these roots always come in conjugate pairs as well. So if you know 1 plus 2i is a root, then another root you already know is 1 minus 2i. Comes in pairs. Please note the 1 did not change signs, only the imaginary parts changed signs. If 7i is a root, then -7i is also a root. If 2 minus 9i is a root, we know it has a root at 2 plus 9i. And in general, if a plus bi is a root, then a minus bi is a root. They always come in pairs. So both the irrational ones and the non-real ones come in pairs. So let's try a couple of these with the imaginary parts. If a polynomial equation with real coefficients has 3i and -2 plus I among its roots, what other two roots must it have? Well, this one tells me that it also must have a -3i. And this one tells me it should also have, whoops, I'm getting ahead of myself. It should also have a -2, and it would be -i for its conjugate pair. So we found the other two roots of the polynomial. Again, that -2 did not change signs. The a stays the same, a plus bi and a minus bi. Only the bi portion of it changed. Here's another one. Polynomial with integer coefficients has roots 3 minus I and 2i. So it's giving us two roots, 3 minus I and positive 2i. Two additional roots would be 3 plus I and -2i. So there are our two additional roots. Okay, here's the super bonus challenge problem. A polynomial with integer coefficients has these roots. Now, when you see a list like this, you need to be really careful that you're pulling the right numbers. 2 minus 5i is one of the roots. -3 minus 2i is one of the roots. The commas are separating these. 1 minus 2, square root of 2 is a root. -7 and 1. Those are the ones it's telling us. So it gave us 5 roots so far. The question is, what other roots must it have? Well, if it has 2 minus 5i, we know it has to have 2 plus 5i. If it has negative 3 minus 2i, it must also have negative 3 plus 2i. Separate it with a comma. The next one it must have is 1 plus root 2, and it must have a root 7. Now this one is just an integer. It's just the number 1. No pair for that one. Remember, it's the imaginary and radical parts that make it have that pair. So these are the only additional roots we know. So last question here says, what's the least possible degree? Well, if we count up the roots we know, it gave us 5 roots to start, and we found a 6th, 7th, 8th, and we found 9 roots. We found 4 more to make a total of degree 9. Okay. Sometimes people wonder, why these imaginary roots even matter. The presence of the imaginary roots is not necessarily visible on the x-axis. So I just wanted to show you these two functions. This one is function f of x. It's a degree 8 polynomial, and it has roots that are exactly the same as this polynomial g of x. Exactly the same roots. But g of x is only degree 4. F of x, the one in blue, has 4 non-real roots. So even though these two polynomials have exactly the same real roots, the fact that f of x has 4 non-real roots really changes the functions a lot. Now you can see when you look at them that they have a similar shape, but if you'll notice the scale, this one has a minimum of almost negative 5,000, whereas this minimum is closer to negative 23. This one has a relative maximum above 6,000. This one's relative max is somewhere around 12 or 13. So those imaginary roots definitely affect the shape of the graph. They definitely affect what it looks like when you graph it. But as far as like the roots that you can see on the x-axis, it does not change those. Okay, second comic of the day. Man, these imaginary numbers, they just lend themselves to all kinds of jokes. So you should read this one because it's also super funny. Okay, we are almost done. We're going to look at 2 more problems right now. You might remember back in Unit 4, if I gave you the real roots of a polynomial, you could use that to write the intercept form of the polynomial, and then if you wanted standard form, you would just multiply that out. So we're going to find a 3rd degree polynomial equation with rational coefficients that has roots of 7 and negative 3i. This is very similar to those problems you've done in Unit 4. We know it has a root of 7. That tells us it has a factor of x minus 7. It also has a root of negative 3i. So we have a factor of x plus 3i. But it's at a 3rd degree polynomial. 3rd degree. We should have one more factor. Well, remember this one, negative 3i comes in pairs. So we also have positive 3i as one of the roots of our function. So we also have a factor of x minus 3i. So here are our 3 factors. This would be the equation in intercept form. Now it doesn't say to put it in standard form because I was not thinking when I was writing the instructions. I do want us to practice putting this into standard form. So when you put an equation into standard form from intercept form, you just need to multiply it out, distribute all those things. When you're doing that, it really, really pays if you pick the 2 that have the imaginary part to work with first. So we're going to multiply x plus 3i by x minus 3i. I'm going to erase this by the time I do all my swoopies. Okay, so x times x is x squared. X times negative 3i is negative 3i x. 3i times x is positive 3ix, and positive 3i times negative 3i is negative 9i squared. So we've multiplied out those first two binomials, and hopefully you noticed while you were doing that we have a negative 3ix and a positive 3ix. Those add up to 0. And maybe you also noticed that we have an I squared here. I squared is equal to negative 1. So if we substitute negative 1 for I squared, we have x squared. And this last term, it's a negative 9 times a negative 1. That's just a positive 9. This is x squared plus 9. Now maybe you already had thought of that because as we've been factoring, I've had you factor that quite a few times, and you knew that that factored as x plus 3i and x minus 3i. So if you just remembered that this is the factorization, you can just go ahead and sort of mentally make that jump. It's just the opposite of factoring. So if you don't need to multiply this out term by term, it is okay if you want to do portions of that mentally. So we multiplied those first two binomials together, and now we still need to multiply by that third binomial. And when we do that, we get x to the third power. We get a negative 7x squared. We get a positive 9x. And that last term would be a negative 63. So here's our function in standard form. Let's just practice one more of those and then we'll be finished. Find a third degree polynomial equation with rational coefficients that has roots of 3 and positive 2i. Well, remember, if it has an imaginary part, it comes in a set. It comes in a pair, so we know that we also have negative 2i. So if we write out a factor to go with each of those roots, we have x minus 3, x minus 2i, and x plus 2i. If we multiply it out, choose those imaginary ones to go first. We get x squared, and again, if you can do this in your head, that's great, plus 2ix minus 2ix, and then minus 4i squared. The positive 2ix and negative 2ix add up to 0. So we have an x squared, and this last term, negative 4i squared, well, I squared is the same as negative 1, so this is really a positive 4. So we've multiplied those two factors together. We still need to multiply by x minus 3, and that will give us our equation in standard form. So x times x squared is x to the third power. Negative 3 times x squared is negative 3x squared. 4 times x is a positive 4x, and 4 times negative 3 is negative 12. So here is our function in standard form. I think on the homework assignment, I also forgot to say that you should put it in standard form. So on your homework assignment, as you're doing it, you should go ahead and put it into standard form. On your homework assignment, on the blue assignment, it's number 10 and number 11 that you should put into standard form. So that's it for Unit 5. Next time we will be reviewing That would be Thursday and Friday this week. Your test will be next week. A day will be Monday, B day will be Tuesday. Please make sure that you come in and get help if you need it sometime before your test. I know you can do really well on this test if you have studied, so if you are finding yourself stuck on some of the problems, please just come in for some extra help. Thank you.